In this episode of Finno-Ugric Machining, we are going to make an adapter for my milling machine for slitting saws. For now I have been using the ER40 collet with an adapter attached into it, and then you have the slitting saw. And it seems to be not rigid enough. At least it introduces some play, some random play into the slitting saw. And I don't like that. So I would like to have it like directly in the SK30 thing. So what we are going to do today is something like this. We make this taper and this, and then this is an ER25 collet. But this end will be turned into a precise diameter, and then you have sleeves which you use for different sizes of slitting saw center. So this will be yeah. So that will be fun. And the material then. Well, well, the material is this. This is, well, I don't know what this is, but this has been the cardan of some heavy-duty truck. The correct name is axle shaft. It is located between the differential and the wheel hub. Well, it's not mild steel, I'm sure of that. It might be really hard to turn, but well, the first thing is that I will cut it in half, and then we have this flame cut surface here. I will get rid of that, and and then I start turning it. Well, I don't expect to have any difficulties with this one, actually. It's it's not carbide. It can be hard, yeah, it can. But as it is a power shaft, you cannot make it really hard, because then it would lose some of its strength. It would break easily, and you cannot break these easily. So let's. I will go out and cut it a few cuts, 2 actually. Okay, that's fun. one of the pieces I got off, and now, I will. I really don't know how this machines. It might be really tough or not, but let's put it there and try it out. Okay, the outer surface is a little bit rough. Well, it's about straight. Now I just tighten this there. I will first face this, and after that I will make here surface where so that I can grip it into the jaws reliably. Oh yeah. That's it. Yeah, okay. After facing now, I'm going to rough this. And well, the final diameter for this this part, the length would be, the biggest diameter here would be of course this 50, but this I don't touch. And then we have the next is 31.75 is the diameter next. And that one I will now rough turn, and it will be from this point here up to there, it will be 63.60, so I will, because this is roughing, I will do it 63. So the remaining 0.6 millimeter I will do after as the final when I finalize this. So now this is just turning and yet turning. I already started here a little bit so that this should be, yeah, let's go to there. So now, enjoy. This must be one of the hardest sheet I have ever been turning. Well, first of all, the chips. Even though they turn blue, let me show you here, we have one. Even though these chips turn blue like this, they are still not crispy. Usually when you get chips of this color, they crumble in your hands, but these, oh no. And it's quite hard, not really hard, but quite hard. And well, but that's actually a very good thing. Now when I get this done to the correct dimensions, I have a very, very stout tool. So yeah, okay. I'll take that. And now, at the moment we are around 40 something. Well, we have 11 millimeters to go from the diameter here now. And The speed is at the moment, I'm using something like 400 revolutions per minute, and the feed is, it's 0.076 millimeters per revolution, and the depth of cut, now I'm taking 1 millimeter from the diameter. This lathe can do it, but not much more than that with that material. This is not aluminium, not at all. So it will be 1 millimeter cuts. Well, 9 more to go, and it's hot. I want it to cool down now. So, our goal here is 32 millimeters. The final dimension will be 31.75, but I will leave that much for the final passes, which is not done with this tool. And the surface is quite rough. 2 millimeters to go. So let's take the first one now. Oh yeah, one thing, when you, like me, I had a cup of coffee and let this cool down. And it loosened the tailstock because this really cooled down. And the thermal expansion, it shrinks and it detaches it from the tailstock. Yeah, and in this case it's a very bad thing because it will cause vibrations. So now we go. And here I have, this is faster now. Wow, what a surface! Well, it's not entirely bad, but it's not good either. Yeah, and it's 400ths of a millimeter oversize, good. 32.04. That's it. And now I will rough the taper by step turning it. So, well, you will see. I don't want to feed this. I want to eliminate as much of this rough turning as possible, because it's really, this is hand feeding. This one is really not a very good idea. But you have to do it at some point, but not just yet. Now I'm roughing this taper by step turning. So the first step will be down to, well, 30 millimeters, and I have changed the angle of this so that I can reach deep enough there. Hopefully this works. It might not. Let's see now. Okay, let's see now. We have here now steps. But yeah, if you compare it to the actual taper, well, there is some resemblance. Yeah, it sure is hiding there inside. Well, before I set the angle of the compound, I will take care of some of these surfaces, take them to the final dimension. For example, this one, which should be, the diameter should be 1707 millimeters. So there is more than 3 millimeters to take off from diameter. And same applies to this surface here and the back surface furthermore down there, which you cannot see. But so, well, I finished that surface already. The diameter is at the moment 31.75 millimeters. Really, it should be 31.75. And it is exactly. My next step is to make this surface here in the back, the back face here. This should be now, I already peeled 0.1 millimeter off from that. Now I should peel off furthermore 0.5 millimeters. And this is a little bit delicate operation. I have here adjusted this so that when this is at 0, this dial, then the tip of this tool is exactly on the surface of that surface. And then I can advance with the compound, and I do this like 0.1 millimeter at a time, because this is some really hard shit. It doesn't, I cannot peel anymore. And the tool is a little bit tilted so that it doesn't start to vibrate. Well, so that's what I'm going to do now 5 times. Bit of mathematics here, because now I'm not going to use model I'm not going to use this to adjust the taper. I consider that method being a little bit inaccurate, actually. All the documents describe this taper, all that I could find, describe it by giving two the length and then the two diameters. That's a very accurate way of describing it, and in this ISO 30 taper, it will be so that the length of the taper would be 42 millimeters, and the smaller diameter is 19.5 millimeters, and the bigger one is 31.75 millimeters. Well, we are actually interested in the difference between those two, which is here I'm marked it as delta. Delta will be 12.25 millimeters. Okay. Well, then we just create a triangle like this one. There is this 90 degrees angle. Then we have a side which I have now marked as X. We don't know how long that one is. Then one side is 42 millimeters, which comes from the length. And this side here is half of the delta. So it's 6.125. And, well, this is just Pythagoras. So to get this one, we take a square root out of 42 squared plus 6.125 squared. And this will yield 42.44 millimeters. Okay. Well, then assume that this triangle is like here. But now we need 100 millimeter long, this side to be 100 millimeters. What will the X be? Well, it's actually very simple calculation. It's 6.125, which is this here, over 42.44, which is then this here. And then divide this by 100. And there you are. Then you get the new X, which is 14.43 millimeters. And now, why 100 here? Well, let me show you. Well, I have a sine bar. This one. This is 100 millimeters. The process needs three components. First of all, this one. This is the height of this is 14.43 millimeters. It's the X here. This. That's one. Then we need this 100 millimeter sine bar, which is this one here. And then I need this to adjust it with the sides of my carriage. Well, then we just put this, and it goes without saying that this, when you do this, something like this, everything should be absolutely clean. Otherwise you don't succeed. Okay, then I put this here. And then this is my machinist square, so to say. I put it together, and I already adjusted this. But what I do, I put this tightly against the side here, and then I push this gently here until it stops. And then I try if I can wiggle it on each end. No, I cannot. Okay. And same from the other side as well. This is just to make it sure. Let's put, like that. That was a little far away. Okay, now it is. And then I again try out. It's there. You cannot wiggle it, just gently push and then you try to wiggle it, and you can, and then you adjust the tailstock, this compound as needed. And now it's very accurately in the position I need it to be. And now, well, we are done. Turning the taper now, and well, I'm feeding with compound this direction, and the carriage itself is locked, and with the cross slide I will feed for each pass 0.25 millimeters. So, yeah. This one I already did. Well, we are almost there. Only a very little bit left here, and after that it's done. I will mark it again here, so I know exactly where we are. Okay. And now I'm feeding only 0.1 millimeter at a time. Yeah, let's go. It's ready. Very good finish, and yeah, okay. It's a good taper. Well, as the last step before going over to the milling machine to do something there, I will take care of this surface. My first thought was to leave this alone, just to let it be like it is, because now it's quite exactly the required 50 millimeters. But, well, the diameter of this surface isn't that critical. It can be a little bit undersized. So I will actually just clean it up. Peel off enough so that I don't have any of these. It's a little bit pitted, and yeah, well, it's easier to keep it clean when it's like that. That, if nothing else. So, milling the slots for the drive dogs in the spindle. And these slots should be 16.1 millimeter wide, and they should be in the X direction, this direction. They should be like 8 millimeters, but since this is a 10 millimeter end mill, I need to put some extra because of the radius. So 13 millimeters down there. And the diameter when these both are finished should be 32.4 millimeters. So these should be milled down to 8.3 millimeters each side. So I have a dial indicator there, which is used to measure the Y deviation, because this mill has a lot of backslash in both X and Y directions. So that was the most convenient way of getting rid of that. So I'm running this 10 millimeter end mill like 500 revolutions per minute, and I'm milling 1.5 millimeter layers at a time, because this material is really hard. So I don't want to strain this setup. Something about this setup, it's just I'm using the dividing head as a chuck here to hold the piece, and then I also can use it to turn the workpiece 180 degrees, because there needs to be another exactly on the other side. Then this is really important to have the tailstock here, because the cutting forces are both ways depending on which side I'm cutting. There will be also torsional forces, because when I'm cutting the end, this end here. So everything must be quite tight and locked. So let's do the rest of this slot now. And I'm feeding this by hand. cutting size for M12. Well, some documents say that it's 10.3 millimeters. Well, this is 10.2 millimeters drill, and we shall see how we do with this stuff. I'm running this rather slow. It will be, well, it will be somewhere around 180 revolutions maybe. This was really hard material, so let's see how this goes. Yeah, and the depth of this hole should be 33 millimeters. Well, deep enough. That was not fun at all. This is like really hard stuff, man. Now, threading this M12 thread here. Well, there is a real possibility of breaking my tap into this hole because this material, well, it's really tough. Well, at some point I did say that it's from a cardan. No, it's not a cardan. It's the power shaft of a lorry. And well, that power shaft is there. I don't know whether it is in English really power shaft, but it's the last thing that connects the wheel to the well, it's the last bit of powertrain, so a lot of torque in this one when it was in its original use. So let's see now. It doesn't want to start even. Now it started. Okay. Oh, it's really tight. Really tight. Oh man. Am I sure I want to do this? Oh, this will be really... I want to position it. Okay. What now? I decided to anneal this darn thing. Well, annealing is actually a very simple process. First you just warm up the workpiece to high temperature, and then you let it cool down. Well, the heat, the temperature should be around, in this case I believe, somewhere around 600 to 700 degrees Celsius, and then it should be left alone, I mean cooled down really slowly. In my case, it took about 4 hours. And after that, well, let's see. Okay, here it is. No more shiny. Well, but it's sure annealed. Or at least I hope so. So, now, well, did I learn something here? Yeah, I did. Never use mystery metals. Let's put some Rockall paste there. Inside there. If I can now get it. This will be hard to get out from there once I get it in. Okay, and then I also dip my tap to that same sheet. Just giving my tap a fighting chance here. Namely, now it will be a make or break. Well, let's see now. Yeah. Oh, wow. Let's see now. Wow, it's still really tough, but man, this is hard. It's tough metal. It's really tough. But it's more manageable. Man! Oh, 10 millimeters more. I think I need to back up a little bit because this might have collected some chips there. Looks like that because we only got 2 of those strings. You should have 3. And that's the point where you usually break your tap when you back it up. These spiral flutes tend to work that way. Oh man. A little bit more. And this is of course where I break the tap. And one more, and then we are there. We are there. Man! Oh. Despite I annealed it, it's still like super tough. Okay. Hopefully, this also means that the tool is durable. Well, it might have deformed my taper. Well, I don't think that's likely, but it might have. Doesn't look like a normal normal threading tap after this. I need to clean this up. This workpiece, the taper didn't suffer anything. It's as tight as it used to be on the milling machine spindle. Huh. Well, that's good. It didn't get oval shaped or anything. Well, good. So the next step is to do something for this end, and this I will turn down to 40 millimeters. Now it's 50. And after that there will be a recess on this end and a thread so that you can attach your plates there. But it looks like my apron needs an oil refill. You don't run this one without oil. That's a bad thing to do. So let's fill it in. So it's up here, and the first thing you have to move the cross slide a little bit away, but I will always wipe this really clean so that I don't accidentally introduce dirt inside there. And I already have some chips in a nut. There is a hex bolt which has some you shouldn't have anything here that goes inside there. So now this cover can be removed by losing 2 screws here. And these screws you don't drop there inside, it would be disastrous. You had to well, take the whole apron apart to fish them out from there. Okay, now when I take this cover off, and I can still see some chips here. Okay, now it's probably okay. So, yeah. And then I have some gear oil, well, and then I just pour it in like this. Something for the bearings and for that one too. And then I just watch the looking glass here down under so that it doesn't need a lot, but there still must be some oil inside there. I usually put it a little bit over the center. There you are. Not more than that. Okay. Well, I don't know. Well, it's totally full now. So this lathe seems to have a total loss lubricating system, much like in steam engine. So, yeah. Now these screws. Okay, that's safely there, doesn't drop anymore. I don't know how many guys have dropped these screws inside there, but that would be a really bad thing to happen. And then I just place it there. And I don't tighten these like crazy again. It's they are just holding this cover on place, and there you are. And now let's see about the side glass. There you have it. It's full. Yeah, about a half a deciliter. Not much, 500 milliliters. We still have 3 more millimeters to take off from the diameter here. Well, the workpiece warmed up, and therefore I had a little bit of a break here. So now, because it has been cooling down, the tailstock must be checked so that it really does a good connection. It does now. And then we go. 0.5 millimeter cuts. And 6 of them actually. Well, now that should be a little bit over 40 millimeters. Well, yeah, hopefully this focuses alright. It's a little bit over 40 millimeters. And yeah, I leave it like that because the final touches for that surface, for one, is done in the milling machine. And yeah, next we will do the chamfer here. But before that, before any tapers, I need to do some cleanup here, especially the floor, which is now occupied by some chips. Well, yeah, well, I have a good method for getting rid of those. Well, nothing more like that. Those cannot be vacuumed because they just clog the tube. I know. These are horrific. They attach to everything. So I hope, as you can see, most of them are now in this brush. And well, so let's see now. We have this collection here. Well, the plastic bag is here. And now the rest of this stuff is actually quite easy. You just wipe these away to the chip pan. And it's almost clean. So, as you see, I already started to make this taper. The compound is at the moment in 25 degrees angle. The correct angle would be 26 something, but this one, well, it should do. We shall see. And of course I'm feeding this with the compound, and yeah, I'm only taking about 0.25 millimeters per from the diameter each time, not more. Well, it's not the nicest blend, but well, it'll do. Now drilling a hole. Well, it will be, this is a 6 millimeter drill, and then we just go. This is now 8.5 millimeter drill. This is the tapping size for M10. And again feeding by hand. like, well, about 250 revolutions per minute. So let's see how sharp our drill is. There you are. Okay. Wow. Well, this is a 25mm twist drill. And the workpiece is quite hot. Well, once again fighting against the odds. Oh man. Well, I need to thread an M10 thread inside there. And how deep? Well, the thread should be as much as this is now sticking out from there. And it is, I give it a little bit less if possible. That much. That much. And now, let's first stick in some of this stuff into the hole. Did it go into? Aha! Man, I succeeded in putting it into the hole. Normally it goes everywhere else, but not in the hole. Oh yeah, okay. And now also I dip this one into this same stuff. Like that. There you are. Oh. Well, the lathe is off. Of course it's off. And we have a slight problem here. Oh, okay, already. So we have a slight problem here. This one cannot turn the full round. So there you are. And now, well, I need to rotate the spindle. It's in the back gear, but I can always free it a little bit and then rotate. Well, let's see. This is going to be mildly said exciting. Well, it started to bind right away. Very good. Not too bad yet. Actually, this feels a lot easier than the first thread I made. Way easier. This seems to be sort of soft. And it's producing 3 chips. Good. Very good. This is like super easy to turn if you compare it to that what we had with the first one. Well, the annealing certainly did something for this workpiece. Basically we are already there, but I will do, just to be sure, a little bit more until I can feel that it's on the bottom. And now it's on the bottom. Oh man. So, typically you would do this kind of operation in the lathe, but I want this hole here to be exactly concentric with the cone. And therefore I'm doing it in this milling machine. So I will rotate that one, and then I have this boring bar, and then I have here a dial indicator which I'm using to measure my feed here, how much, and now of course, because we are measuring direct, it means that every millimeter here will yield 2 millimeters in the diameter. So, well, at the moment the diameter is 25.98, something like that, and our goal is 27. So we have about 1 millimeter to go. And yeah, let's put some cutting oil here. Then we just start. That's it. Surface finish is absolutely gorgeous. Well, let's measure it. Well, there is nothing much I can do if this is now wrong. So, we are 1/100th of a millimeter oversized, which is very acceptable. I should take care of the outside because, well, if you look at it, it's not straight. So what I would like to do here is to straighten it. And, well, front side or back side. So now we have this. It is it's I would say usable tool. You have the taper. It was amazingly it fits there like really well, and now it's certainly running through. Making such a thing that has two parts on different sides, making this running through in a lathe, so that it's concentric all the way. Well, the only method I really know of is to turn it between centers, so then you can turn it around. But then this recess here, how do you turn that one between centers? So now, I also measured this one, and it's it's 3 microns at the moment to play here. It's about it's not much. And then I of course tried it so that I turned it 180 degrees to figure out whether this taper is somehow crooked. It's not. This is a really usable item. Well, now I just need to do some caps here to hold the slitting saws. Well, it's a good item. Well, this about concludes our this episode of Finn-Ugric Machining. Well, we shall see what will come up the next one. Till then, bye!